Okay, so formally I welcome you all. Good evening. It's really my great pleasure to welcome one of the emerging star researcher in this field of Skyrmionics, dear colleague Dr. Hariom Jani from Department of Physics from the Ariando Group of National University of Singapore. So he has done very nice work, and today we will get a glimpse of it. Yeah, good morning. Good afternoon, good evening, wherever you are. I'm very delighted to welcome you all and giving a short introduction about Hariom. So he is actually having a senior research fellow position at the Department of Physics at National University of Singapore. He obtained his PhD from NUS in 2019. And his research interests are quantum material, topological spin textures, antiferromagnetic spintronics, oxide electronics, ionic control, and so on. Although he is very young, but he has already got several awards and honors to his credit. I'm just pronouncing a few of those. In 2015, he got the Outstanding Alumni Gaurav Award from CIRS from India. In 2018, he got the Arthur Noack Teaching Award from MRS of US. In 2018, he got the Graduate Student Research Award, Silver Medal in MRS US. In 2021, he got the Young and Brilliant Lecture Award from European Physics of Magnetism of Poland. And 2021, he also got the Physics Breakthrough Prize by NUS Physics Department in Singapore. And he's really working on very interesting topics, and this particular antiferromagnetic spintronics. I'm really delighted to welcome you, Hariom. I just like to mention a few things in case there are new audience. That during the lecture, we don't take any questions. So if you have a question, kindly write the question in the chat box, or at the end of the lecture, you raise hand and we take one by one. Also, at the end of the lecture, I would request all of the participants to switch on the camera. So that means Hariom need to stop sharing for a minute. And after taking the photo, we will continue the question answer session. So with this brief introduction, Hariom, I'd like to now invite you to start your lecture. Thank you so much. And by the way, I should not forget to also express my thanks to my team member. So the team of WTS working hard to make these seminars possible. My team members Braj, Puspendra, Shakti, Azhar, and so on. So on behalf of everyone, I'd like to express my thanks to you and everyone. Yeah, so please start whenever you are ready. Thank you very much.
First and foremost, thank you, Prof. Vedanto, for the kind invitation and the entire WS team for putting this together. I'm extremely thrilled and excited to interact with budding young researchers in India and overseas. And I hope I get to share a little bit of some of the recent work that we have done, as well as some of the work that is just coming out from our team that I hope you will find exciting. And the theme of my discussion today pertains to antiferromagnetic skyrmionics and how we can go about perhaps developing a potential candidate platform to realize this. Evidently, there are two aspects to this field. One is antiferromagnetism and one is skyrmionics. So let's just take them one after the other. Skyrmionics is something that we are all increasingly getting familiar with. However, just to bring everybody on the same page, I'll just like to share a very brief introduction. Firstly, a skyrmion essentially is a whirling magnetic texture, which can be seen here, for example, as a projection of spins on a surface onto a flat plane. This in particular is called a hedgehog or a nail skyrmion. And in actual samples, this would actually propagate in the third dimension. Typically, a simple equation like this is good enough to describe the spin variations, but more essentially, we use this entity called the topological charge to quantify some intrinsic property. We obtain this by doing the integration of the local solid angle spanned by the vector field modulo 4 pi. And this is a very interesting property that if you have spin textures which wrap the unit sphere, obviously you would get a value 1 or some -1 or something like that. And if you wrap only a hemisphere, you would get half, and so on and so forth. So with that basis, let's now look at what are the various textures and how do we go about creating the nomenclature of these objects. So the first thing is the nail skyrmion that we just saw, which has topological charge 1. We can then obtain the block variant by doing an azimuth rotation by 90 degrees. We can also then have the inversion of the azimuth to get the anti-skyrmion. Note that this has an opposite sign. And the unique feature to note is that the sense of the rotation as well as the core orientation at the center of these whirling textures determine this topological charge. So if, let's say, you were to flip the core from up to down, the signs of the topological charge would also change, but the magnitude would remain the same. However, if we were to only project to the hemispherical entity, for example, inside this white ring, we now get a nail meron and likewise an anti-meron. And these are structures which have topological charge plus half or minus half, depending on their core orientations. Now, the interesting feature about the entities in the bottom row is that they have their spin orientations away from the respective cores lying in the plane. As you can see here, they're all white in color, which is lying in the plane. However, in the skyrmionic cases, we have textures lying out of plane away from the core. So there is some kind of fundamental difference between them, but from a geometry point of view, you can see how they're all correlated with each other. When it comes to merons and anti-merons, then we can now play a very simple kind of algebraic game of combining these textures. For example, a meron and anti-meron with both the cores up, having charges half and minus half, would then result in a topologically trivial structure where the total charge vanishes. And this is called a trivial meron pair. However, if we were to flip the core orientation for one of these entities, then we would land up getting a non-trivial texture. And this is called a bimeron. Note that a bimeron can also be obtained from a skyrmion by applying a 90-degree rotation in split space, right? So there is a very nice relationship between all these textures. And this is not entirely surprising because we know that as far as we don't do any harsh treatments or we don't cut the spin textures in a harsh manner, we should always smoothly be able to rotate from one texture to the other. With that out of the way, let's now look at what can we do with skyrmionic textures. Firstly, they have been proposed to host information in racetrack kind of structures, the hallmark idea proposed by Stuart Parkin more than a decade ago now. And this is still one of the most promising interests in this community. It is also then possible to envisage combining individual quasi-particles to then create logic and memory applications because they can interact with each other. And more elusively, it may be also possible to investigate non-von Neumann architectures, for example, reservoir computing or neuromorphic computing by looking at skyrmion fabrics. So it is really promising to work with these entities and textures because they have this unique winding behavior, which allows them to be intact structures and therefore move around and avert annihilation at defects, etc., much superior to typical domain walls. Now, ferromagnetic skyrmions, which is typically where the skyrmionic community emerged from, have specific issues. Firstly, that they are extremely susceptible to external magnetic fields because ferromagnets have strong Zeeman interactions. They also undergo sideway deflection, like the Roberto Carlos football kick, when they're driven by currents, they don't go straight, but they actually go diagonal sideways. And this is called the skyrmion Hall effect. While this is a very interesting physical effect, it has detrimental issues in devices. And also the scaling of these textures cannot be that dramatic because of the fact that the dipolar interactions in these systems are very long range. So to address and alleviate some of these limitations, the community has looked more recently at antiferromagnetic alternatives. Now, what are antiferromagnets? Well, as the name itself suggests, these are made up of structures with oppositely aligned ferromagnetic sublattices. Usually, there are more than one. I should just correct a typo here. This is minus, my bad. So here we have these entities which are oppositely aligned, and we then get to define an order parameter called the nail order, and this is intrinsic to the system, and this is non-vanishing. If you add these two entities in anti-parallelly coupled structures, they would be zero, but their difference would be non-zero. Now, this actually endows some merits to antiferromagnets such as robustness against external fields, the presence of dipolar fields, which are rather short range, and dynamics, which are in the ultra fast regime, which then have very interesting effects. So if we combine the field of antiferromagnetism and skyrmionics, then we get this idea of antiferromagnetic skyrmionics, which was this very hallmark proposal made by these two theoretical papers almost 6 years ago. Now, the merits, of course, are that these structures would then be stable even in the absence of external fields. They would be very robust. They would not undergo sideway deflections, as shown in this very nice image here. And also, the absence of long-range dipolar fields would then allow very aggressive downscaling, and therefore we can pack information bits into small regions. But the added benefit with antiferromagnetic skyrmionics is that textures can now approach speeds of kilometers per second. This is very fascinating. And as shown here, these speeds are proportional to the current density driving them and inversely proportional to the Gilbert damping. So if we can really find systems with low Gilbert damping, we can achieve strong speeds. Interestingly, not just skyrmions, but even bimerons exhibit the same kind of tendencies and behavior and have the same potential applications as much as skyrmions. Very interesting work has emerged in the field of synthetically coupled antiferromagnetic stacks, which basically involves two ferromagnetic layers which are coupled via RKKY interaction in an opposite manner. While this does mimic some aspects of antiferromagnetism, the RKKY exchange itself is usually significantly weaker than that found in natural antiferromagnets. So it is really interesting to then look for antiferromagnetic skyrmionic textures, which then would enable us to really make benefit of these properties. In this search, we tried to investigate an entire topological family, and that is what our recent work has been all about. Indeed, we do find these textures, and the approach that we use to do this is called the KIBBLE-ZUREK mechanism. One aspect that you should note is that the textures I'm going to be discussing henceforth are topological, not in the magnetization, but in the Néel vector, which is M1 minus M2. When you keep this in mind, you will know that they have the same kind of mathematics, but of a different vector field. Now, let's look at what the KIBBLE-ZUREK mechanism actually is. This was proposed almost 50, 60 years ago by this guy called Kibble, who suggested that if we start a system above a critical transition or a phase transition in the disordered phase and we drive it across, we find that right below the transition, we would have emergence of local order in pockets. However, these pockets would be uncorrelated with each other until, of course, the system completely goes beyond a phase transition, and this order becomes very large, and we have different pockets which meet each other to form some kind of domain boundaries. He proposed this in the field of cosmological physics, but this has some very interesting ideas in condensed matter physics. In principle, because if we have a system possessing some kind of unique symmetries, for example, Mexican hat potential, then we could exploit the availability of special meeting point of these domain boundaries, which have the winding of the local phase in a complete 2π orientation, and in which case you would land up trapping a topologically non-trivial entity at the center. This has already been observed in a variety of condensed matter systems, and we were thinking that if it's possible to do that in antiferromagnets, then we would be able to make this critical breakthrough, which has been difficult to make in antiferromagnets because they are very difficult to work with. In order to convince you what's happening, I'm firstly going to show you a simulation that we have done by using atomistic parameters of an interesting material system, which I will just reveal in just a bit. Now, the simulation shows just the top layer of the antiferromagnet with the spin Z components. So I will just start off the simulation. As you can see, the order is pretty random here at the moment, all kind of red and blue orientation. But as we run the simulation, very quickly enough, order starts to emerge. And after very short time scales, we actually see that most of the system has settled in. Then we have very specific structures. Now note that there is a direct correlation between the structures that I showed you earlier, such as merons, antimerons, and bimerons, with respect to what you're seeing here. And therefore, indeed, as we were hypothesizing, it may be indeed possible if we can drive this kind of a phase transition in a material system. So let's look at some of the key parameters that are required and then see what material fits these. Firstly, it should be nearly compensated magnetic sublattices. It should have this U1-like symmetry or easy plane anisotropy so that all the orientations of the spins are nearly favorable. We should be able to perform this phase transition. The system should have low Gilbert damping. So eventually, hopefully, we could drive ultra-fast dynamics. It would be interesting also to have correlated degrees of freedom. We will discuss this later in the talk, where this can be a very useful tool for us to tune the parameters. And eventually, we also want to drive these textures and move them around electrically, and therefore we should have spin injection driven effects. We think that we have found a strong candidate which satisfies these criteria, and this is alpha Fe2O3 or hematite. Now, very curiously, this material is also the main element in rust, and it is therefore earth abundant. Now, this material satisfies the first criteria because it is a canted antiferromagnet, and it has already an easy plane anisotropy at its room temperature state. It has accessible phase transitions, and it has ultra low Gilbert damping, almost comparable to some of the best ferrimagnetic garnets. It is also a transition metal oxide, and therefore it has coupled spin, charge, and lattice degrees of freedom. And finally, some recent works have also shown that by exploiting spin Hall effects, by using a heavy metal overlayer, we can actually drive spin injection into the system. So with that, let's look at what's happening in the physics of the system. Firstly, we have the dominating interaction, which is the antiferromagnetic exchange, allowing the system to go from the para to antiferro state. We also have the Dialoghinsky-Mori interaction, which allows the canting of the sublattices. Note that the D vector characterizing this lies out of plane, so the canting is in plane. And this results in a macroscopic canted moment, which is observable in magnetometry, although it is quite weak. Finally, we also have the magnetocrystalline anisotropy, which then favors specific orientations in the system. For example, at room temperature, it lies in the in-plane state. And this is because the system actually has competition between two terms, the magnetic dipolar interaction and single ion. If we look at these equations, it's a very fascinating dependence. One is the expectation value of the spin Z component squared, and the other one is the expectation value of the square of the component. So the temperature dependence of these two terms is almost similar but slightly different. And we find that in Fe2O3, these two terms are almost similar but opposite in sign. And this has this unique benefit of therefore driving a phase transition from easy plane to easy axis, which is available in temperatures close to room temperature. More crucially, we also have this trivial state at low temperatures, topologically speaking, and a rich state which exhibits U1-like symmetry above the MORIN transition. And therefore, exploiting this transition, which is much more accessible in comparison to Neal, it would be possible then to drive the KIBBLE-ZUREK physics. So with that, let's look at some experimental techniques. Firstly, we use this technique called experimental X-ray photoemission electron microscopy, with X-rays coming in grazing incidence, and then it generates photoemitted electrons, which allows the generation of maps. So I'm just showing this very well-established body of work done in coupled ferromagnet, antiferromagnet objects, in case you're not very familiar with this technique. And as you can see here, if we come in with circularly polarized X-rays, we can map ferromagnetic objects. If you want to study antiferromagnets, you have to look at linearly polarized structures. The processes is first and second order respectively, and while the former maps the magnetization, the latter maps the Neal order. Now, the curves that you see here are basically the X-ray absorption spectra, and they are fundamentally different because one is a ferro and one is an antiferro, a metal and an insulator. And as you can see here, these textures allow us to create a map of these entities, noting in the ferromagnetic case that opposite textures, for example, black and white, would be corresponding to spins that are exactly opposite. However, in an antiferromagnet, because the structure, whether you keep it like this or you keep it like this, it is the same, you can't distinguish north-south, and you can't distinguish east-west. And therefore, both this entity would itself look purely dark, and the perpendicular entity would look light. Whereas in this case, there is a 180-degree rotation. Here it is a 90-degree rotation. This effect is very important because we will see that this has some important consequences on the data interpretation. Interestingly, we use the same technique of vertical and horizontal incident X-ray polarization onto the sample, and due to the relative angle between the polarization and the Néel order in the system, we can then create a systematic map of these textures in the system, because there is a well-established dependence due to this relative angle. So phi is the relative angle between the polarization and the Néel order, and by mapping this, we can actually color and identify the orientation of these textures. This is something that we will use later on in the work. The growth technique is pulse laser deposition, and we grow ultra high quality layer by layer growth of Fe2O3 on sapphire. This is very funny because, you know, we almost say we grow rust on sapphire, which is a very interesting combination. But this is crucially because it's an isostructural compound and they share the same corundum structure. We also have high quality STEM images which confirm the good quality of these samples. Now, one important factor I just need to mention is, of course, that we actually have a platinum overlay on top, because it acts as a conducting surface, which is important for the PEAM experiment I mentioned earlier. When we do the imaging at low temperatures, which is below the phase transition, we notice predominantly purple structures, which we understand to be out of plane, which are separated by yellow-orange regions, which evidently should be domain walls. And therefore, you have out-of-plane domain, a domain wall, and then an out-of-plane domain. So you have this rich domain walls, which are sort of separating these domain structures. As we now warm the system further, we have widening of these domain wall regions and shrinking of the out-of-plane regions. At the same time, these green circles indicate the emergence of local order in the system due to the proximity to the phase transition, and evidently the nucleation should reveal that this is a first order phase transition. As we continue to warm the system, we now at the end land up at room temperature with predominantly yellow-orange structures, but curiously, we see these little bubbles or dots, which are indicative of out-of-plane cores, which are still trapped in the state, which should not be typically present. This is exactly what we were intending to create with the phase transition, and therefore we investigate this with a systematic study. We do this by doing the angle-dependent experiment that I mentioned earlier, and we create these rich RGB maps. As you can see here, red, green, and blue correspond to 60, 120 degree separated structures. However, due to the limitation of the linear dichroism technique, we cannot resolve up-down, as I had mentioned in my slide earlier. For example, these two green structures or these two blue structures, but each of them themselves can be resolved very well. So as we can see here, the in-plane structure is very strongly undulating, whereas the out-of-plane structure has these little bubbles. And when we compare exactly at the same location, we find that the bubble is trapped between some kind of whirling texture. So let's zoom into some of these entities. For example, at the bottom here, we have the white bars indicating the Néel order. And shown in the schematic structure here, we have the circulating entity, which would then correspond to a block meron structure. We then have this pointy structure in the direction outwards, which would then correspond to a Néel meron. And then we have this kind of a diverging structure, which is an anti-meron. So we now see evidence of these textures here. Apart from this, we also have pairs of entities, for example, as seen in these two images, which could now be a topologically trivial pair of merons or a non-trivial pair of merons. However, because of this modulo 180 factor that we have in linear dichroism imaging, we can't resolve the exact orientation of the core. So we don't know which one is which. Nonetheless, the fact that these structures are very stable, there is bound to be entities which are topologically rich as well. Now, with that established, we wanted to confirm the nature of these textures. So when we perform circular dichroic imaging, which is supposed to pick up, mind you, ferromagnetic entities, we find that there is no contrast in the sample whatsoever. And this confirms that the textures that we are seeing are of the Néel order, not the magnetization. And therefore, the vector field N here corresponds to the Néel vector, not the magnetization. Next, now, in order to discuss that we have stabilized this topological family, can we now tune and control them? So we firstly do this by chemical control. Now, as you can see here, this phase transition is sitting roughly at about 220 to Kelvin. While this is very interesting for physics, in order to do real applications, can we bring this to room temperature? And it turns out that we can do this by doping heavy element sites, heavy elements at the ion site in the system, which then brings the transition smack at room temperature. And when we reinvestigate the KIBBLE-ZUREK physics, we actually managed to get the same cores and bubbles that we had shown earlier. When we compare the size evolution of these textures, we found that very simple models are able to then recreate the temporal evolution of this, primarily based on the exchange stiffness and the anisotropy in this material system. And because the anisotropy undergoes a vast change because of the in-plane to out-of-plane orientation, basically the K changes sign. So you have this divergence, and then you have the formation of the antimonons on the right side and domain walls on the left side. By rhodium doping, we can of course shift this entire structure and also change the dimensions in a very dramatic manner. So the system is indeed very promising and very versatile to tune the states as desired in particular device of choice. Next, we go on to discuss the evolution of these textures in freestanding membranes. This is now a slightly different technique. Instead of using electrons that are photoemitted after X-ray absorption, now we actually use transmitted X-rays in transparent samples. The polarization of the X-ray is now horizontal and is incident normal onto the sample, but we are able to reproduce the same exact evolution due to the relative angle between the polarization and the Néel vector. Now, shown here are these freestanding Fe2O3 membranes, which are held on silicon nitride silicon support, shown in this optical micrograph here with a heater, which we use for in situ temperature control. Firstly, we find that the temperature evolution of the system from magnetometry is almost identical, and that we are also able to, below this transition, create the same domain wall structures, which then evolve into the same topological cores and entities above the phase transition. This is very promising because firstly, we have managed to detach ourselves from typical substrates which are very restrictive. For example, in my previous discussions, I showed the use of sapphire. While it has a very good template, it is not compatible with silicon technology. However, if we are able to create these freestanding membranes, we can then transfer them to desired platforms of choice. More crucially, we can now exploit flexure or curvilinear geometries to tune the antiferromagnetic textures, and this is something that will be coming up in our work very shortly in the future. Next, having discussed how to generate and control topological textures, in the next 10-15 minutes of my talk, I will briefly talk about how do we identify what lies ahead. We first start off with this important problem of detection. The techniques that I've shown you before involve the use of synchrotrons. And while they offer great insight into these textures, they are not very versatile when it comes to throughput and fast processing. Hence, it is crucial to see if we can do the detection of these textures in a lab-based setting. And we do this and realize this with quantum magnetometry. The idea is to use a very specific defect in a diamond lattice. For example, by doping nitrogen, we create a vacancy, and this paired entity has the spin triplet configuration with these spins ms +1, 0, and -1. And the interesting aspect about them is that their relative shifts in energy between them is precisely dependent on external magnetic fields with a very specific correlation. Now, if we are able to use that field to perturb this defect, and we are able to read the state of where this quantum state of this defect is, then effectively we would then measure the stray fields. The key enabling experimental tool for this is photoluminescence, and this is because the ms equals to 0 state has strong photoluminescence with transitions to much higher order energy states, whereas the ms plus and -1 have lower photoluminescence. So by mapping photoluminescence that is emitted by this NV, we can effectively re-identify what is this stray field component projected along the NV axis. And this becomes a nice imaging tool when integrated with a scanning tip, typically what we use with, for example, AFM. The only difference is that this tip is now made with diamond, and we can then use this to perform magnetometry by integrating a laser on top. This work has been done in collaboration with the group at Cambridge, led by Anthony and Mike in the NUCLEATING group. Now, in order to understand how this imaging works, let's revisit the physics. Firstly, it is important to note that we have the Dzyaloshinski-Mori interaction, which causes the canting of the sublattices. As you see here, M1 and M2 are not exactly anti-parallel, but just slightly canted. This angle psi is very weak. It is almost 1 milliradian, so it is really, really small, but it is sizable enough to have a canted moment which is non-zero. This canted moment is, of course, given as M1 plus M2, and this results in the texture detection that I'm going to discuss now. Firstly, if we have a topological texture as shown here, as you can see, this is a rotating whirling texture oppositely aligned in M1 and M2, which is a block Meron. The nail order would be exactly the same replica here, for example, following M1. However, the canted moment now behaves very differently. Note that by the very symmetry of the two L and M should necessarily be perpendicular to L because these are all unit magnitude entities. Therefore, M actually behaves like a nail Meron, and any texture which has non-zero divergence of magnetization would generate stray fields. This is electromagnetism 101, and therefore can be sensed by an NV sensor. The important aspect to note is that typical sensing such as MFM may not be able to pick up this weak stray field because the moment is very small. However, NV has the capability of being sensitive to extremely small fields and is therefore very powerful in this regard. So when we perform this experiment at room temperature, after having already done the KIBBLE-ZUREK transition, we actually see data something like this. Now, to understand this, let's break it down into small parts. We firstly look at this entity here, for example, a red blob, and the red blob is, mind you, indicating a strong Z component of stray field. So then we have to back propagate the stray field to then work out what the structures are. And then we have done some simulations here to indicate that if the canted moment follows these arrows here, as shown the nail Meron structure, it would then generate a strong red entity. Likewise, if we have the arrows now of the canted moment flipped outwards, the entity would turn blue. So this arrow is now showing the canted moment, and therefore the nail vector would follow the 90-degree off setting. So nail textures would correspond to block textures, which is why I have written them on the top. It's not a typo. The interesting aspect about this technique now is that we are able to do something very different from what we were able to do in X-ray techniques. This is because we are able to resolve the chirality of these two textures apart from each other. And this is very promising and something that we can't necessarily do in the X-ray approach. Furthermore, we can now look at these textures such as these crossing points having a quadrupolar structure, and this corresponds to now an antimeron. And pairs of these entities would necessarily then result in the formation of bimerons. So this entire phenomenology of textures can be mapped in a lab-based setting, really improving the throughput and the capabilities. And this is something very fresh and new. Hopefully, you'll get to see this also very soon. Next, we have the discussion of the novel antiferromagnetic textures in the system here, and that is motivated by some form of theoretical studies. This is done by my colleague Jack at Oxford in Paolo Relli's group, where we use micromagnetic simulations to approach, to investigate the tuning of the exchange, the anisotropy, and now a new symmetry breaking term, which is the interfacial Dzyaloshinski-Mori interaction. Note this is different from the natural Dzyaloshinski-Mori interaction in Fe2O3, which is not interfacial, that's bulk. But we wanted to see what the effect is. Mind you that this kind of an interfacial effect we're looking at would break symmetry and would therefore enable stabilization of chiral textures. This is simulated by having stacks of anti-parallelly oriented ferromagnetic slabs, which is then a very good approach to simulate these entities. So if we were to look at this temperature evolution of this structure, if we were to be in the state above the MORIN transition, we would actually find the stabilization of male merons and antimerons. Note the key factor here is that we don't stabilize block merons anymore because they are now homochiral, and the antimerons now undergo distortion due to the symmetry breaking term that has been added. Of course, these entities can also form pairs to form male bimerons, and the dimension, the intercore separation distance can then be tuned systematically by tuning the exchange and the anisotropy, and therefore temperature variation can provide a very facile handle to tune these textures in the system. More crucially, we were also very interested to see if it's possible to stabilize skyrmions in the system, which have never been done before in an antiferromagnetic scenario. And that's what we investigated here. And it turns out that this is indeed possible. We find that there is a wide range of exchange and anisotropy systems natural to Fe2O3, which allow the system to be stable, and certain regions which allow it to be unstable. Also, as you can see here, we are able to widely control the dimensions of this texture, really pushing it to the smallest limits within the micromagnetic approximation, mind you. And this is very promising. By tuning all these three parameters, therefore, it is then possible to realize, at least theoretically for the moment, these Neal skyrmions. And the most encouraging aspect of this result is that when you see the D values required for this IDMI, this is almost comparable to what people have seen in ferromagnetic skyrmionics. So if we use the right ingredients and we have the right approach to create the samples, we are quite confident that it should be possible in the near future to create Neal skyrmions in the system, therefore really mapping out the entire gamut of topological textures in the antiferromagnetic family. Lastly, the question of reversible control, and this is very important because we need to now harness and use these topological textures once we've created them. So the first idea draws from, builds up rather upon our work of rhodium doping. As you can see here, we go from the transition at low temperatures to almost room temperature. The question we asked ourselves, can we do this in a reversible manner? Because once you put any chemical dopant, you can never sift out the dopant and then bring it back to the original state. So was there a possibility of doing reversible doping? And it turns out this is possible, not by using rhodium, but by using the lightest of all elements, hydrogen. What we now show here is another body of work that we have done very recently, where we again start off with the system exhibiting the standard phase transition here, and we do hydrogen doping into the system by performing catalytic spillover across these platinum nanostructures, which then allows hydrogen molecules to be cleaved into nascent hydrogen, which are very reactive with the host, which is the Fe2O3. Once hydrogen enters into the system, we find the landscape to be dramatically different with no transition whatsoever. When we do X-ray absorption studies, we actually find that this is indeed lying in the plane, for example, at the cross points here. And then if we dehydrogenate the system, then we retrieve the phase transition again. You know, it's like that movie where you are able to make something disappear, but the best magician is somebody who can make it appear back again. And so this is a very important tool to do a reversible control of the phase transition by using hydrogen, and therefore this is certainly very powerful. However, one key limitation, of course, is that we have used a catalytic spillover process. So this is not very scalable or device friendly. However, very nice work from other groups have shown that by integrating proton or lithium pumps with ferromagnetic devices, in their case, they've used cobalt to go back and forth into various ferromagnetic states, they're able to realize this. So in principle, the same physics can then be repeated on the antiferromagnetic thin films, and we can drive this with electric fields, which is much more device friendly. Lastly, we've talked about electric fields, so it's interesting to ask about electric current control. And necessarily, the fact that if we have a heavy metal which is present in adjacent to a ferromagnetic or a antiferromagnetic layer, it allows the injection of spin currents into the system via the spin Hall effect. This has been demonstrated very nicely in nickel oxide, for example, and also with Fe2O3 adjacent to platinum, allowing varying form of antiferromagnetic domain control. So in principle, if we are able to harness this and recreate these topological textures, in principle,
We expect electric current control to tune the antiferromagnetic domain landscape and eventually even drive these textures to these unprecedented kilometers per second kind of speeds, which would be very promising for various skyrmionic applications. So with that, I would like to thank my colleagues, collaborators, and my mentors who have played a very pivotal role in our research. Also, the team from Oxford, Paul Rodelli, who has been a very close collaborator, and his team, as well as all our colleagues at various synchrotrons and our colleagues at Cambridge. With that, I would like to briefly share that we have written a small review on various skyrmionic systems that are emerging in correlated oxides and what benefits they are, which I'm showing here. If this interests you, you can find it here. What we have discussed today sits in this part of the space diagram. There are various rich other correlated oxides which host other kinds of systems. And finally, with that, I would like to just share the key takeaways. Hopefully, I've convinced you that Fe2O3 is a promising platform to build antiferromagnetic skyrmionics. This is really just the beginning phase. There's a lot more research journey to tread, but I'm sure it's very exciting. We also have the ability to harness the KIBBLE-ZUREK transition to reversibly generate topological textures, widely tune their dimensions and orientation, and also enable their realization in freestanding membranes, which is very critical to move towards silicon-friendly platforms. By integrating symmetry breaking DMI interactions, finally, we would be able to also obtain homochiral antiferromagnetic textures, which would ultimately be important for some kind of direct control. And with that, I would like to open the floor to comments, questions, and discussion.
Okay, thank you, Hariom, for this excellent talk. So on behalf of everyone, I clap for you. I think there are several senior colleagues like Professor Anjan Barman and others are also here. Many thanks to them. So I request all of you to switch on your camera, and Hariom, maybe you can stop for a second the sharing. I request all of you to switch on your camera so that we can take a group photo. Hello, Ananda. So, yes. Okay. Hi, Chandra. So, others are coming up slowly. So please bear with me for a few seconds. Okay, so let's smile. Cheers. One more photo. 40 people now. Okay, so I request all of you to switch off your camera. And Hariom, please share your screen again. Sorry for the trouble. And before we take the questions, I like to just briefly mention that next week we will not have any W2S seminar, but next week between 8th till 10th, 3 days, we will have a very interesting Indo-Japan workshop on spintronics. So you are welcome to submit an abstract. Tomorrow is the deadline. Hariom, if you just stop sharing for a second, I like to show it just quickly because some people leave in between. So this is the conference I'm talking about next week. Interface phenomena for spintronics, very focused topic. So a lot of interesting speakers from India and many interesting speakers from Japan are giving talks actually, and anybody is welcome to attend or submit an abstract for a poster presentation. We will have a very interactive poster presentation. So in case you are interested, please submit an abstract by tomorrow, or at least register if you want to get the information about the conference, and we can share you the link for the talk. Yeah. So Hariom, I'm sorry, you can now share your screen again. And let me see, there are questions. Right now not, but I would like to begin. I mean, I have many questions, very interesting talk. Just to begin from towards the end, the micromagnetic simulation you showed, there is an archive paper. So it was done with what kind of platform? Like it is atomistic or?
Mumax.
And but this is about antiferromagnetic. So Mumax has.
That's a very good question.
To do that.
That's a very good question. So this is one of the hurdles that we had to overcome, because micromagnetic approximations inherently are good in the range of long-range order, and therefore they are good for ferromagnets. However, when you have this special type of arrangement of structures where you have anti-parallel layers which are adjacent, but within the plane they are ferromagnetically aligned, for example, in the cubic community, we call them A-type antiferromagnets, then we are able to still continue to use micromagnetic approximation with certain caveats. So fundamentally, micromagnetic approximation is only useful when you're discussing finely stabilized, energetically stabilized entities, not to discuss dynamics. But this is okay in the context of the discussion that we've done here. And we paid special attention to the role of the demagnetizing term. And we find that as far as an antiferromagnetic system is concerned, in this arrangement, the most significant effect is to actually contribute a local anisotropy, very much like the magnetic dipolar term, which I shared very early on in the physics of the system. So we do manage to use this tool and yet generate these various textures without going to the atomistic limit. So it shows the capability and the power of this approach, but also there are very clear limitations that need to be kept in mind.
Okay, so the details are given in that archive paper, how you have taken.
Yes.
Okay.
Absolutely.
So in a way, it's like synthetic antiferromagnets, where you are considering each layer as a ferromagnet, and you are taking advantage of the coupling between them. Okay. Exactly.
That's very nicely put. Because the only difference then would be that the interlayer exchange is then much stronger in the natural antiferromagnet case than in the synthetic cases.
Okay. Well, I don't see questions by others. Maybe the talk was very clear, but I have a few more questions. In the beginning, I think a small correction when you talk about the ferromagnetic order and the antiferromagnetic order. If you could go to that slide, please.
Which one?
I think little bit go down. Little bit go down. Not this. There was like go down, please. There was something like a ferromagnetic order, antiferromagnetic order. Then you say first order, second order, maybe.
Ah, yes. Okay. Yes.
Yes. So I think there is a kind of interchange. The ferromagnet is second order transition and the antiferromagnet is first order, isn't it?
Oh, no. This is not the phase transition that I'm talking about. I'm talking about the detection by X-ray absorption. So when the X-ray come in, X-ray circular dichroism is actually a first order process. But when you're looking at, and the reason why you say that is because you're directly probing the M. However, the linear dichroism probes M squared, and therefore it is a second order process. So although the net magnetization in the system is 0 for an antiferromagnet, the M squared in the system is not 0 because of the fact the Néel order is not 0. And therefore, you would still be able to detect that by linear dichroism. So this is not phase transition. This is just the process of interaction between the X-ray polarization and the magnetism.
Yeah, thank you. I got confused. So others, if you have questions, please raise hand. Yeah, I will take the question now by Professor Anjan Burman. Please unmute, show your video and ask your question.
Yeah, I just joined a little late, so I probably missed some part of it, but it's very nice talk. I have a quick question regarding this meron, bimeron, and antimeron. So do you see all these phases in the magnetic phases in the same system under different sort of magnetic field or different temperature? Or I mean, are they stable? For example, bimeron, are they as stable as a single meron or an antimeron?
So what we are now finding is that we actually have a fabric of these topological textures which are created in tandem across the phase transition. And so simultaneously, we can see merons, antimerons, and of various helicities and chiralities, right? This is important to note because there is no intrinsic symmetry breaking term. All these textures are stable simultaneously. However, in order to specially favor one over the other, then we would have to insert the IDMI, which is what the subject of my the micromagnetic discussion was. But here, as you can see, all of them are stable at the same point and same time.
Okay, so I mean, do you see a meron antimeron annihilation? I mean, when they come closer together, I mean, and does
That's
that
a very
occur locally or sort of globally?
That's a very interesting question. So this data is something that I've not shown here. For example, we actually perform field evolution of these textures. Given that the system has a canted magnetism, we can have a weak Zeeman interaction, significantly weaker than, for example, synthetic antiferromagnets or natural ferromagnets. So when we apply ex situ fields, we actually see that for small fields, there is no effect on the system whatsoever. But when we apply really large fields, we actually have a large scale annihilation of these textures. And this is typically driven by Miron anti-Miron annihilation in the system. Although, as you can see here, there are still some entities which are still present here, even at after annihilation for very strong fields, which is a natural behavior of antiferromagnets. So indeed, as you rightly say, there is Miron anti-Miron annihilation present in the system. We have some other simulations also which reveal this effect. However, if we have the symmetry breaking chiral term, then we would be able to stabilize homochiral entities which are stable without annihilation whatsoever. And of course, as you can see in our experimental data, also we have these entities stable simultaneously without annihilation. So in principle, this is possible. Yeah.
Okay. Thank you so much.
Thank you.
Yeah, thank you. So I have actually a question. The lower image, which having the spin texture, it is simulated data or it is an experimental data?
So this data is obtained by using the vertically polarized X-rays. Yeah. And this is obtained by a composite image of various in-plane orientations of the X-ray polarization with respect to the sample. So we actually collect 6 images of the sample by using horizontal polarization, and then we stitch them together to then create a composite angle-dependent map. So you're seeing the composite result of all that put together.
So it's basically,
so this is not a simulation.
But this is like a simulation of the experimental data. Yeah.
This is experimental data.
Experimental data, but somehow kind of simulated. Yeah. Because how do you otherwise get these spins? So you have.
So this technique is called vector mapping. So you basically would map the various orientations of the sample by rotating the azimuth of the sample, and then you would put all the intensities together by correlating the intensities across all the angle relative between the polarization of the X-ray and the nail order. And by doing that, you would be able to assign a specific color, for example, red, green, blue, which would then add these values. Yeah.
Okay, it's a kind of standard program to analyze extreme images, isn't it?
So ferromagnetic contrast is pretty standard, but antiferromagnets, this is one of the very newest approaches that has just been very recently developed.
Okay.
So usually what people do is they would just show a single image, for example, as you see here, but there is a possibility of obtaining a vector map of all these spin orientations. And that is what this technique allows us to do. So this is basically what I was highlighting in these 2 particular papers, particularly developed by our collaborators at Oxford.
Okay, thank you. I don't see other questions. So I can ask one more question. If you show some slides where there are like thread-like, images, I think from, like this. So here. So in, the 360-degree domain walls, they also look very much similar. So they will be just like thread because the contrast outside and inside are same. So how do you differentiate that these are not 360-degree domain walls?
Just to clarify, are you talking about low temperature or high temperatures?
194 Kelvin, for instance.
Let me just clarify. Do you mean 180 degrees or 360 degrees?
360 degree. Because the magnetization, let's say on the left and right side of this yellow rope-like feature, string-like feature are same. So they are called 360-degree domains. So because the magnetization is same, so it's a 360-degree rotation. So what are these? Okay, let me reframe my question. What are these threads like structure?
So these actually do separate out of plane domains, but they are 180-degree walls. Because a 360-degree, I'm not able to imagine what a 360 structure would look like. But here, for example, you have an antiferromagnet, for example, up down on one side and down up on the opposite side. Okay. And so you would rotate from one to the other, which is separated by a 180-degree wall, which is what these objects are. So this is a topologically trivial 180-degree domain wall, as you can see here. Yeah.
Okay, but let's say if you do an in-plane magnetized system, then you know the magnetism, the purple color will basically tell either up, I mean right, or and if you have another color which will tell left. I don't know why in a perpendicular system you are getting, let's say, up down as also purple and down up as also purple. It should change, isn't it?
Because it's an antiferromagnet.
Okay.
If it's a ferromagnet, you're absolutely right. You would see these two colors as separate colors, right? So which is what I was trying to discuss here. In this, sorry, let me go in this imaging technique. Right, so if you see here, in ferromagnets, you would resolve up and down, or for example, pointing in these two directions is black and white. But here, up, down are both black.
Okay. Now I see. And,
Yeah.
and that image was taken in XMLD mode, yeah?
Exactly.
Okay, then it's clear. Okay, thank you. Anybody has any question? I still see Professor Burman has raised hand. Is this old? Okay, he has taken it out. Are there questions
Sorry.
from anybody else? Seems not the case. It's very interesting talk and very clear actually. You have made a wonderful presentation. So I think we can probably kind of wrap up. I like to share my screen to present you a small memento, digital memento. I hope you can see my screen.
Absolutely, yes.
Yes, so on behalf of my team, we like to present this to you for your excellent talk and thanking you for joining us. I read it for you. W2S Seminar Webinar Series on Spintonics, National Institute of Science Education and Research, NISER, Bhubaneswar, India. Takes pleasure in presenting this plaque to Dr. Hariom Jani from National University of Singapore in recognition and appreciation for being a valuable speaker to give a lecture on building a platform for antiferromagnetic skyrmionics. So thank you so much, Hariom, for your excellent talk, and really I appreciate your time and efforts to join this W2S platform. So as I said, next week we will not have any W2S seminar because we have this Indo-Japan conference, but you are more than welcome to join it, listen to talks by eminent speakers, and participate in the discussions. And next week after that, we will again resume the W2S activity, same day, Thursday, same time, 8 p.m. Indian time. Until then, please stay safe and see you next time, either in the Indo-Japan conference or W2S. Thank you so much, Hariom. Thank you all, everybody, and stay safe, stay healthy. See you next time. Good night. Have a nice day. Bye-bye.